Hi, I'm Jay Marshall. Welcome to the first Physna Podinar.
Chris, I think your digital twin algorithms have a bug. Welcome to the first ever Physna Podinar. I am actually Jay Marshall, and that was Dr. Christoph Roedig, physicist and engineering director here at Physna. Now, he'll be joining me a little bit later to dive deeper into the actual mathematics behind what we do here at Physna. We'll be doing that after our interview with Dr. Michael Grieves. I do want to thank Chris for helping kick off our series here with that little digital twin joke. I hope you enjoyed it. Now, in case you think you were hearing things, I did in fact just say that this is a Podinar. When we wanted to start building some educational or edutainment type material here at Physna, we very explicitly did not want to prescribe to the typical corporate webinar format where it's, PowerPoint, messaging, product. We also didn't want to just do the standard podcast format where sometimes that can just turn into random chatter. We want this to be a series of content where we invite experts from some of the most innovative areas today. So 3D printing, digital twins, smart manufacturing, robotics, machine learning. We don't want to lock ourselves into any one format. We also wanted to be able to just have some fun. So we kind of made up Podinar. So we hope you enjoy what we came up with here, and subscribe, ring bells, all that fun stuff to check out all of our future episodes. And please leave us comments. Let us know what you would like to see here at the Physna Podinar. Now, for this episode, you likely saw a headline or a title that referred to a fireside chat with Dr. Michael Grieves, but you probably also don't see any fire here. So why don't we start by fixing that. All right. Well, Dr. Grieves, thanks so much for joining us here on this first ever Physna Podinar. It's kind of half webinar, half podcast format. I'm not going to do the kind of the typical, hey, somebody that needs no introduction and ask you to introduce yourself. So maybe instead I could say, all the work you've been doing for the past 20 years in this space and the latest activities of the Digital Twin Institute. Anything you want to share with everybody, kind of what you've been working on and what you're excited about now?
Yeah, so I think there's a lot of interesting things going on. I mean, obviously this has been named one of the top 10 technology initiatives of the 21st century. And so there's a lot of parts and pieces to it. There are some things that I'm particularly interested in. One is certainly on the education side. I think that there's some need for education, both kind of at the operational level, but certainly at the executive level. I think that asking executives, hey, spend $1 gazillion to do this new stuff is a problem. And I think that we need to get the executives up to speed. I mean, they are not digital natives. And some of them have what I call retirementitis. Please get me to retirement so I don't have to bother with this. But quite frankly, that doesn't work. Certainly the idea of how do we move the technology forward, common ontologies, common structures, cybersecurity is a big deal. And so those are all things that I'm working on. I mean, I think that you can basically throw a dart in the wall and hit a bunch of, certainly hit any area that needs some attention in terms of moving this forward. So all those things are of interest to me.
No, that's outstanding. It's funny you mentioned education. I know my background kind of in the enterprise, almost application development, business application space, that digital transformation term. And when you say digital natives, it's kind of the case across the board, all aspects, let alone the things that you refer to as digital twin. In fact, one of the things that I kind of go back to a lot, a blog post that you had posted in December there that we had chatted about. You have this image where you show kind of a rocket and its components, and it says physical underneath it. And in fact, maybe we'll try to illustrate it here. I'm going to do the magical trick where I do this now. And then on the other side, it's basically the same image, but with a bunch of zeros and ones. It says virtual. And then the kicker to me is you show kind of data going in and information going out. And I think that it's such a great, simple image. But for folks that maybe aren't as kind of familiar, maybe kind of give them an overview of kind of what that cycle looks like, because I think that's a really central key to understanding this space.
Yeah, so it's a simple model, but I think it's kind of explanatory of terms of what we're trying to do. I mean, we've always had physical things in physical space, okay? And physical world trumps virtual world any day of the week. I mean, we since time immemorial have done that. And the interesting thing is that as soon as we sort of had an idea, we had to put it into physical form so we could communicate that idea to other people. And so the physical aspect of it is pretty time consuming in terms of doing it. And have it in virtual space that, in the last 50 to 70 years, we've started to be able to do with computers and put this into digital form was, I think, just a huge step forward because we're looking at trading off bits for atoms, and atoms are very expensive and keep getting more expensive if even the cost of inflation, and bits keep getting cheaper thanks to Moore's law and our advancements there. We obviously need to capture data from the physical space because that populates it. I mean, where this differs from the video games and things like that is it has to mirror our reality. It doesn't do us any good basically say, yeah, we're going to fly in virtual space when that doesn't happen. Jump off a building in virtual space and you may be able to float to the ground. It doesn't work.
Infinite surrounding parameters that could be variable at any point in time.
Correct. And so we need to capture the data because we need fidelity of that in virtual space. But we want to be able to use that information in physical space because the information, as I've said, is a trade-off for wasting resources. Not for the resources I physically need to do that, but everything over and above that. So if I have real information, it's a trade-off for the physical resources that I expend over and above the minimum amount of resources that if I was omniscient and omnipotent, we would basically expend that. Now, what's kind of interesting about this whole thing is yes, this is a kind of how we want to create. We have the physical world that we're given and the virtual world that we're creating and we're keeping in sync. But quite frankly, it's the virtual world that gets created first. I mean, nobody walks into a factory at some fun and saying, pounds the metal and says, gee, I hope an airplane comes out of here. So we want to start off in the virtual world because we can basically do things much more efficient and effective than we can in the physical world. There used to be a joke at NASA that NASA's goal was faster, better, cheaper. Pick two. And so I think we're in the position of being able to pick all three with respect to being able to model and simulate the physical world, and then do as much work there as we possibly can. And only when we get it all right, as my colleague from NASA, who actually coined the term digital twin, John Vickers, has said, what I want to do is create the product virtually, test the product virtually, manufacture the product virtually, support the product virtually, and only when I get it all right do I want to go out and move expensive atoms. Yeah. So that model works throughout the whole life cycle of the product.
Well, I think one of my favorite kind of quotes of yours that you shared directly in one of our earlier conversations was your story that basically by 2075, you think we're going to be 3D printing aircraft carriers. And I just love that because, 3D printing in the last handful of years, you talk about Moore's law. I mean, what you can get today for $500 is actually pretty impressive compared to 5 years ago. But when you fast forward, when we're 3D printing steaks already, right? So I mean, if I were to,
I'm not sure about that one, but
well, I'm sorry, we're not. I saw somebody is. How's that? But it's happening at least, right? But if I were to kind of sit back and say, okay, so on a scale of 1 to 10, if a 10 is 3D printing aircraft carriers, all these data points we talked about, business context in and out, if that's a 10, and a 1 is, hey, I got some 3D models in a virtual environment with some sample data that's helping me run simulations. Where would you say we are on the kind of that scale of 1 to 10?
So let me sort this out and unpack it a little bit. Is that, first of all, I picked 2075 because nobody's going to find me at that point in time. So I'm safe.
Well, me either. So say whatever you want. We'll both be right or wrong.
They might find my digital twin, but he's not.
Nicely played.
So that was about moving atoms, quite frankly.
Okay.
I mean, the whole issue is that's about being able to move atoms in a digital 3D printing that is much tougher to do. I think the kind of earlier opportunity is to basically create this virtual environment that is reflective of the physical environment.
Truly reflective.
And so it's so whatever I do in virtual space is what's going to basically happen in physical space, and I think that occurs a lot earlier. So I don't think you have to wait for 2075
Sure.
actually get some real value. Now that said, I think we're still at the really early days of being able to have the fidelity and granularity. So I'm thinking we're 2, maybe 3 in terms of kind of where we're at. I mean, the thing I wrote in the blog is the idea of categorization and comparison, and we only scratched the surface, and certainly even on the comparison side of the ability of being able to do the same sorts of things that we could in physical space, i.e. go along and say, that's the same, that's the same, that's the same, that's different, than we could do in virtual space. And so once we start to be able to do that, I mean, that is I think a critical requirement that we have. And we're basically just starting to get that. You mentioned the purchasing piece. I mean, until a purchasing person can sit there at his desk and then see all the possible things he can buy in the world that looks like the thing he wants in both form and function, we're still a ways off. So we've got a lot of room to go. We also have the ability of the fact that all these models are kind of different. And so how do we have digital twin models that I can say, I'm going to take this part and that part and that part and put them all together, and they're all going to be an assembly.
Yep.
So there's a lot of work to do in this particular area.
Well, and the reason I wanted to phrase it up like that is it's more that, again, I think for folks, even people that have been in manufacturing and maybe are still kind of in a frame of mind that, hey, the current process works great, or maybe it is just going a little bit further down the path of 3D. Again, there still seems to be a lot of open-endedness around the term and where it starts and stops. And so hearing it's maybe more of a 2, or even if it was a 3, or even a 4 for that matter, right? Some people might think it's an 8 or a 9, especially if you look at some of the marketing out there. Now, if it's something where to get from, say, that 2 to a 3 or a 3 to the 4, are there any areas or focus areas or specific things that you think folks could focus on to kind of get to that next stage towards that kind of desired end state?
Yeah, so I think, as I said, there's a lot of opportunity here, but let me make sure that we're clear on this, is that the digital twin is for the entire product lifecycle, okay? So where it starts is as soon as I intend to have a product, okay? And it's got to be a product I really plan on manufacturing. So if I'm in the magic carpet business, I'm probably not ever going to be there. But if I'm going to make a plane or a pacemaker or oil rig or anything else, okay, as soon as I intend to do that, I want to do as much of that work in the virtual world as possible. My digital twin exists from that point in time.
Yep.
And the beauty of the digital twin is once I stop manufacturing, in fact, all the physical products can go away. I still have the digital twin of it, and I can use it. I mean, one of the examples that I talk about is a guy sitting there at JPL looking out his window and seeing people throw stuff into a dumpster from one of the old probes and saying, maybe I should use some of that. And it turns out that it was valuable. I think it was Viking that they were throwing out, and he was looking at one of the new probes, and he actually went dumpster diving to pull that information out. And that's what happens with physical stuff, but with digital twin stuff, it doesn't. But as I mentioned, some of the areas that we've got to wrestle down are, and I know this kind of scares people, but ontologies. I mean, how do we call things the same way so that your product is my part and somebody else's assembly? And so we have to have sort of either common or mapping languages to do that. Then how do I have different digital twin models work together so that I actually can compare it? Now the idea of being able to compare just forms without having to worry about what structure they're in is a big deal. I mean, and I think that's going to be a huge opportunity to say, I don't care what the underlying structure is. I don't care what CAD you're using. I have this form and I can compare this form with every other form.
I think to your point, it's that's one of the things that when we build our catalogs for folks, right? Everybody kind of gets their own individual sandbox and their own dedicated compute segment inside of Physna. And so having the ability to know, look, it's not a shared model where everybody gets to see everybody else's 3D models. But for some of these customers that have, hundreds of thousands of models, for folks that have been doing this for dozens of years, that's pretty standard. But how many of those duplicates? How many, to your point, I say this in one of our overview videos, I talked about part ABC is the same as part XYZ because our ERP system thinks they're different because that's what we called them, but they're the exact same part. And so I think some of those components, I think some folks don't realize that even just that single bit of hygiene, not only are you reducing the number of parts for your designers to use as part of a broader assembly, but again, supplier costing, different price points, that can really start to drive deduplication, drive down costs. Could even have impact on kind of different environmental aspects if you can actually shrink your utility bill. There's all this stuff that kind of can come along for the ride, even though, again, for a lot of folks, it's just, well, that's the 3D models that we use to design and build the product. But to us, we feel like we could fold into that digital twin discussion by being that thread. And that's why we've appreciated you obviously going on some of these conversations with us.
Yeah, so remember, as soon as I produce a new part, I produce a whole family of costs. I mean, I produce a new supply requirement to purchase stuff, new inventory, new liabilities in terms of product liability, new insurance. I mean, it's not just simply the cost of, oh, gee, I've just created a new design. I basically spawn off a whole family of costs that take a life of their own.
Well, and the certification, I know, especially in automotive, and certain components have to go through. We've heard numbers from like $5,000 to $25,000, kind of the all-in cost just to certify a part. So it's like, well, if I can just use one that's already there, that already kind of has that stamp on it, I'm already $25,000 ahead of the game right there. And so I think it kind of feeds back to some of your earlier comments about, the whole PLM life cycle, not just CAD or not just, searching, but it's part of that broader business conversation.
I would contend that at $25,000 is probably the cheapest part of that whole family of costs.
But if you do that times 1,000, right?
Inventory and the cost of maintaining that. I mean, I think $25,000 is cheap. I mean,
yeah.
Those costs will just jump up in size.
Yeah, and I think it's interesting because I think from our perspective as well, it's not, the word silos tends to be such a bad word, but I think some of this stuff, it just happens naturally over time. So some of the data exists in different places. So whereas designers are concerned maybe a little bit more about, building the right building the perfect part. Now, you know what, I'm going to save 20 minutes and just redesign this. Procurement would probably love to save all that money, but those insights just aren't there because, it's not their job to know the difference in the parts when you get to some of these manufacturers. So it's like, again, it's not silos in a negative way. It's just been a natural evolution. But again, if the digital twin brings this together.
So I think it is silos in a negative way.
Okay. Well, you can say that.
in that, quite frankly, unless it has different functionality, okay, it ought not to be made. Okay, so the individual engineer tinkering with a part just because he doesn't like the aesthetics of it, again, he creates a whole new cycle of costs. And if he hasn't done anything with the functionality of it, why would you do that? And I think the problem has been, I don't know what else is out there, and I have no good. So I'm looking at part numbers and trying to match a description of that part number with what I'm trying to make. And again, humans aren't very good at that. Right?
Yep. Well, it's funny. I do sometimes joke. I'll say, I'm trying to build the better lug nut as a way to illustrate, because that's how it kind of starts almost at every level, right? So I think it's a great point, well taken. Is there any one thing that if it's somebody that's kind of in this area, is there something kind of burning, whether it's hey, don't, if you're getting started down this path, do this or don't do this, or hey, if you've just gotten started down this path, watch out for this gotcha. Is there any one thing that kind of really burns in your brain that you kind of want to get out there to folks that might be watching this that you think has been very consistent that you want to kind of get out there for everybody?
Yeah. So I mean, I think it goes back to sort of the original discussion. Is it's got to be driven by value. I mean, pick the use cases that you're going to do, and I mean, the second piece is don't try to boil the ocean. So pick low-hanging fruit that you can basically have, a better than 90% chance to say, I can make this work. If you go into management and say, give me $100 million and I'm going to, give you nirvana, you're going to find yourself looking for a job pretty quickly. Okay? You certainly have to get the $100 million.
Yeah, right.
So I think that at the start, incrementalism is good. Look for a use case, get the value proposition right, so you can say, look, if I do this, I'm going to, save this, X amount of dollars, or produce an information stream that's going to be of value to us, and then and start there as opposed to, it's grandiose. I'm going to solve all our problems at once here.
Yep. Well, I know we're coming up on time here. I also want to make sure, again, so appreciative of you joining us here today. Is there anything else you would like to throw out there? Either it's maybe events you're doing or things that you'd like to throw out for our audience dialing in here today?
Oh, there's a couple groups out there that are doing a pretty good job. ASME has a Digital Twin Summit that I think you mentioned before, and we've gotten some pretty good talks out of that. The second thing is that there's a Digital Twin Consortium that is doing some decent work. I think there's a lot of actions there. And I guess the last thing I want to do is to basically say, look, the digital twin doesn't start to exist when something rolls off the factory door. I mean, by that time, it's a little late. You've lost the whole opportunity at the front end. And quite frankly, in fact, I've got a thing up on my ResearchGate website that says why that's a fallacy, okay, for a number of reasons. And so I think you've got to take the broader view of the digital twin. And in fact, it didn't even have a name to begin with. I called it the underlying premise for product lifecycle management, because it really is meant to be in all aspects of
the whole
lifecycle.
Yeah.
Everything. So I think that's kind of you need to be looking at all those parts and pieces. And again, one of the issues, and you just alluded to it with a word I don't like, is siloed. If everybody has their own version of the digital twin, you're going to lose a hell of a lot. And so that's why we want the digital twin to exist across the entire product lifecycle. I think part of the problem is people think twin and think identical twins, and the only requirement for a twin is that it has some simultaneousity over its life, and that it's going to be similar. I mean, it doesn't require that they both have to exist at the same time.
Right.
So I think people get confused. And in point of fact, when I hear somebody say, "Well, it has to be identical," but remember, it just has to have two of them existing at some point in time, and they have to be similar.
Yep. That piece of it does seem to be the crux of some of the confusion. And so I think that being able to clarify that so that people aren't being hindered in getting started because they feel that end state is so far down the line that, you know what, I'm just going to go back to building the better lug nut, right? So, well, this is great. Well, Dr. Grieves, again, thank you so much for joining us here today. You've been a great partner with us these past couple of months with a bunch of these conversations, and I look forward to talking to you again soon.
Great. Thank you very much for inviting me.
Thanks, Dr. Grieves. All right, so before we move on to our interview with Dr. Roedig, for those that maybe aren't as familiar with Physna yet, I invite you to check out our Physna Enterprise Deep Dive video listed in the description below. Now, this video is a ton of fun to make. We shot it right here on my farm, got to play with some of the equipment around here. But one of the best aspects of putting this together was getting to illustrate firsthand the benefits of searching the world of 3D with 3D. And whether you're a manufacturer of farm equipment or in the automotive or aerospace industries or basically anywhere that uses 3D, how this innovation can help reduce complexity in your environment. We have a handful of hands-on product demos being launched that go even deeper into this technology. So make sure you check it out. Okay, so now I get to introduce you to Dr. Chris Roedig. Now, as mentioned earlier, he's the engineering director of enterprise products at Physna. He's also the graduate of The Ohio State University and carries his PhD in physics with a focus specifically in ultra-fast atomic and X-ray physics. And we didn't want Chris to feel left out, so we interviewed him in front of a fancy fireplace as well. Hey, Chris.
Hey, Jay, how are you doing?
Good. Hey, seriously, thanks again for being the first Physna special guest on the Physna Podinar. As much as I don't really necessarily like to prescribe to standard interview questions, probably does make sense to maybe start by telling everybody a little bit about yourself and what you do here at Physna.
Sure, happy to do so. So I went to school for physics, which led to graduate school. I was mainly focused on experimental physics, and towards the tail end of that, I was interested in working more in industry, and I sort of bounced around a couple startups. I worked at a healthcare IT startup in town that grew very quickly, so I learned a lot about growth and leadership on software teams. And sometime last year, the year before last, Physna started coming around, and it looked very interesting because here was a very high growth startup happening in town here, and but it was also more fundamental, in terms of technology. And I thought that was really interesting. It was closer to what I had imagined I'd be doing back when I was in graduate school. So I said, sure, why not? Let's go try this. And so and now I'm here.
Awesome. Well, and I think, in your role, especially with your background, and being able to dive even deeper into kind of the mathematics of what we do at Physna, I think that one of the concepts that's kind of resonating with folks is that kind of concept of P&A, right? Taking physical objects or 3D models, turning them into code. And the metaphorical reference to DNA, even if it's not kind of one-to-one, it kind of seems to help flip the switch for folks, searching and comparing and kind of getting down to the root of things. And I know the process is kind of our secret sauce, but, wondering if you could dive just a little bit deeper into kind of how we do what we do and kind of how Physna works at a more kind of mathematics level.
Yeah, sure. So when you think about DNA, not in the sense of the sort of building blocks or the assembly manual of a cell or an organism, but think of it as a way to tell if two organisms have a trait in common or have a common inheritance, as a way to mark that very, very precisely, right? And it does get used that way today. We see it all the time. So what we approach with our indexing is similar to DNA in terms of the marking and detecting common inheritance and common traits. And the way it works, basically, imagine you took the object, every scrap of it, broke it apart in just the right way that it makes sense, and then assigned each little piece of it a unique code that only that piece has. And then if you say, I have two, then you can take those individual fragments, those little indexes, and you can shove them in a database. And so if you're interested in finding what other objects have this exact little feature, like the one I'm holding here, you can now ask the database that in a pretty straightforward way, because we went and broke the object into millions of tiny pieces. We gave each one a very unique label. And then what's more, the more of these pieces the two objects have in common, the more they're related, all the way up to they're literally the same thing. And so the analogy here is what information about something complex can you use to say that the two complex things have some traits in common or have some common inheritance? And the inheritance thing works quite well because a lot of what we do is we try to help designers find variations of something they designed. They're designing something and they're trying to make a version of it for a different customer or to fit with a different version of whatever it's being installed into. And now they're able to say, find me all of the variations of this part I designed, and they will find everything that has some exact geometry in common. And what's key here is that we're able to reference one-to-one by exact geometry. So if we find something, it definitely is related. It definitely is the same part or a part that shares exact geometry in common. And we do that in a way that is very scalable, because it's similar to how DNA is basically one long string of code. So is the index that we make from our 3D geometry.
Well, and what I love, again, about the metaphor, I know that, for example, if there's a ball bearing that's encased inside of an outer shell, things like shape searching or even computer vision wouldn't necessarily find that stuff. But to your point, because we're able to do the entirety of that geometric object, we're actually able to find that, which I think is fascinating.
Yeah, so what's really fascinating is that the way we do it, it really doesn't matter where the thing is, if it's inside of another thing, if it's upside down, how it's oriented, because we're basically breaking this thing down into little pieces, parts that are uniquely tagged. So imagine you took whatever it is apart, you labeled everything very carefully, and then you threw it in a bucket, and then you looked for it using those labels. And so we don't need to rely on sort of second order things like computer vision that can only see the outside of something. We truly just take the thing apart. What's really great about this is that it doesn't matter where that ball bearing is, whether it's inside of something, if it's upside down on the back end of it or the front end, because we're not looking at the object that way. It's in the same way that when you're looking for a word in a long string of text, it doesn't matter where that word is in a sentence, it will find it. And so we've simplified this idea of searching 3D shapes into something that is has all the advantages of text search, but it's still a 3D search. Yeah. And if you took, let's say, an imaging approach, now you have to teach your computer vision machine learning system to ignore the thing that's around the ball bearing. If you took other approaches, point clouds or what have you, they don't really know where the ball bearing starts and ends. What we do is, because we break everything down and at a layer of abstraction where we can still understand the geometry, we're able to serialize this ball bearing basically into an index, and it really doesn't matter where it is, what's in front of it, what's behind it. None of that really matters when we search something.
And again, to one of the key use cases that we tend to talk about with customers is the fact that the duplication of those kinds of parts. So something like a ball bearing, it's a good example in some ways. There's going to be a ton of them, but no matter what the part is, it could be a door panel, it could be a fastener. In fact, it kind of triggers my brain. Another thing I wanted to ask you about, I've been in this industry for 25 years now. I started in the enterprise, spent the past 10 years in big tech. What really lured me to Physna was that we're kind of literally almost creating a market. The whole searching 3D with 3D, really has the potential to be that kind of proverbial game changer. But it's kind of also that engineering prowess. So like folks such as yourself or your team, the pace of innovation. One of the stories that I heard before I joined was that one of our customers were taken aback by, kind of the core Physna technology, but they wanted to extend it into classification of parts. So like we were talking about a second ago, like these 5,000 are fasteners, these 10,000 are bolts, those 1,000 are panels. So the legend is that you basically went in about a weekend or so, you had a working prototype of a complete machine learning based classification system to do just that. So like, tell me how that happened, like what triggered you, like explain, or even that functionality in general, like explain what you actually built there.
Yeah, so, well, first off, it wasn't just me, it was me and a handful of really talented engineers.
Well, your team, sorry.
Yeah.
Yeah, I didn't mean just you. You're great and all, but I meant your whole team.
Yeah, the team. Yeah, so we had been working with this customer for a while, and It was actually, they showed us what they do. When you go to scale and you're making tens of thousands of units a year, and you have a huge engineering team, like 3,000 mechanical engineers, whatever, you get a big mess in your with your digital assets. And and I was fairly new, and I just saw this for the first time. So one of them showed us a spreadsheet, several thousand lines long and maybe 80 columns wide. And that spreadsheet was meant to just help them understand fasteners. So screws, just screws.
Okay.
It was screws, every length, every type of head, every thread, material, et cetera. And the person at this company said, well, could you help me? I did this for screws. I cataloged all our screws. But there are so many other parts where I don't even know where I should start categorizing. And we downloaded around 2,000 parts from them, various mechanical parts that you might buy when you're building a machine or something. And we said, can we come up with a way to automatically group these into buckets, so that way someone would know, hey, I have a lot of washers over here. I should start paying attention to washers. And so we just tried that. So we wrote some code to pull out some geometric features, some data about the parts, and we threw that into a machine learning data warehouse, and we ran what they call k-means clustering. Like, break this into a small number of groups, put all the like things together. My analogy was, let's say you had a big bucket of random screws in your garage. I know I do. You probably have one in your barn. And you said, I don't know what's in here, but I'm tired of looking at it, and I keep running to the store for more screws. So I'm going to go and dump these out, and I'm going to start sort of, okay, here's the wood ones, here's the metal ones, here's the long ones, here's the ones I don't know. And then you start refining those, right? And you say, okay, now I got all these wood ones, and some of them are gray, so they're probably meant for outside. We basically created a system that does that. Given an unknown pile of stuff, it sort of breaks it into groups, and that then gives a really nice starting point because the user can then say, hey, you did find all my washers. I'm going to tell you those are washers and tell you to go look for more of them. And now the system's kicked off, it's trained, it's learning, it's predicting, and it's solving problems.
Yeah, and what I love about that as an example, and I wanted you to explain it a little bit more in depth, is because the term classification on the surface might seem pretty straightforward because people have been trying to classify their parts for a long time. But when you threw down that Excel spreadsheet example, I'm guessing a number of folks watching us maybe even cringed a little bit because that is still the tool of choice in so many of these situations. But I mentioned with Dr. Grieves in our earlier interview that, customers of ours that have 500,000 parts, one customer has over 1 million parts. And when you start talking about having to have humans do that classification versus, I love your bucket example, and that made me cringe because of what's in my barn, like you said. But that ability, again, metaphorically to say, look, I have 20 buckets, and having machine learning decide which buckets they should be in and how that can help cut down the time to do that classification, which then makes searching that much easier in the future. So I love the way you kind of lay that out. It's been pretty popular so far, right? I mean, it seems to enter almost every customer conversation.
Yeah, and it's neat because it complements the other search modalities that we have. So we have the geometric search that I talked about earlier, where you're looking for the other thing that has that shares exact geometry with what you're looking at. What is the other versions of this thing I just designed? And that's the ultra precise end of the spectrum. And then the classification is on the other side of what's roughly in the same category as this. But what's neat is these categories are defined by our users. And so that way they adapt to whatever makes sense for their line of business. Is it motors versus batteries, or is it washers versus screws, wood screws versus metal screws? they get to set up models that can tell apart these parts into whatever categories make sense for their work.
Yep. Concept of searching is starting to take on a little bit of a different shape, if you pardon my pun there, within Physna, because it's not only a text search or searching with a 3D model, it's classification. We can do 2D to 3D with photos. It really does take that 3D searching to a whole new level because, again, to your point, there's all these different modes in which we can help you get to the bottom of what you have going on in your 3D assets.
Exactly.
So I'm going to ask you an even easier one here. You're actually in our new Physna headquarters in Columbus, Ohio.
Yes.
I love the new logo on the wall. What's with the green stuff?
Oh, so that's moss. I hear.
So that's actual living moss.
Yes, it's actual living moss. Yeah, it's pretty cool. It's
Yeah, the
dry,
whole office looks incredible.
Yeah, the office is great. This is our inaugural day. First day at the office.
So first Podinar ever. You're our first Physna guest on the Podinar. It's the first day of the new office. I think we're onto something here.
Yeah.
Well, let me ask you this then. So with all this great, awesome new stuff going on, besides the moss wall and the new office, what would be the one thing you would want people to know about Physna that maybe they don't know from either our overview videos or even just personally your own experiences here?
So the way we work here is pretty exciting, right? So I'm speaking from engineering. It's a combination of the fast movement you need in a startup, where the product is changing shape daily, and we move fast, we prototype, we build things quickly. We keep our processes lean, keep our teams small, and deliver quickly and collaborate with the customer very closely. But on the other hand, we're doing, in some cases, some hardcore R&D. We have machine learning engineers who are building totally new kinds of image classifiers and machine learning systems. We have computational geometry engineers who are working on these algorithms for indexing 3D geometry. And so you get to experience some fundamental research, actual R&D engineering, math, but bring that to products in the same week. So that's pretty exciting.
No, and it echoes back to my earlier comment around kind of how quickly something as complex and seemingly industry shifting potentially as classification. The fact that you all were able to say, okay, our customers are asking for this, and you threw resources at it in a very short amount of time, being able to bring that value directly back to the customer.
Yeah, and that example specifically, which is kind of typical around here, we not only did we have to figure out how do we take what's important for classification, how do we get that out of the geometry and send that off to a machine learning system. Now we had to figure out, well, how do we get all the plumbing around that working? We ought to give it a UI. Our user doesn't really know about this, so they need to work with something vaguely familiar. So now we have to work with designers to present an experience that makes this usable. We also have to figure out how to do it at scale, right? These companies that have this problem also have a lot of data. So we're talking tens of thousands, hundreds of thousands, sometimes over 1 million models in their database. And so whatever we do has to work at that scale. We have to, in sort of one motion, think of all of that all at once and make one decisive increment that touches all of those facets of product development: scalability, R&D, usability, and bring it back to the customer quickly enough to get feedback to make sure we're solving the right problem for them. And that's pretty exciting.
Well, I think absolutely. And even then on top of that, for some folks that might be thinking, well, what about things like material type or other data? We have integrations with PLM. We've been talking to folks about ERP because obviously there's lots of costing data or other business data in there. So you all have been continued to be amazed and humbled by the innovation that's coming out of you and your team. So I'll personally thank you.
Thank you.
In the context of what we've been doing, because the customers, again, obviously we're turning things around in great time for everybody, and hopefully others will experience that as well here. So I learned something new about you here when preparing for this Podinar, and that's you used to do some movie making in college. So this is kind of the wild card question for the day, right? So if we were to shoot a Physna movie, what would the story look like, and what character would you play? Like, you're already a doctor, so you're kind of halfway there on the whole killer supervillain name thing. So what would you do?
I'm not sure I know how to answer that question.
How about just a supervillain name?
The supervillain. Oh yeah. He's in Knoxville. Some barn. And he's trying to build a time-traveling tractor, but
in his barn, part-time,
yeah.
in his copious free time.
Yeah. And and he can't. That bearing, he just can't find a replacement for that bearing. He knows he has it.
It's the bearing of doom that's going to kill us all. And I just can't find a way to that's awesome.
Should the villain be using Physna or the good people?
Oh, no. No villain would ever use Physna. Physna will conquer the villain and bring world peace and all kinds of other goodness.
Okay, so maybe the guy in Knoxville's not the villain. He's like the humble superhero with the time traveling.
Very humble with a terrible receding hairline and is wearing a man girdle under his jacket right now during this interview. I don't know if any of that's going to be usable, but that's pretty great.
That's about what I would have come up with. So the thing in college, I wouldn't call myself a filmmaker. It was a competition that anyone could enter, and it was just sort of like you had a weekend to get it done. And so a bunch of us who knew nothing about filmmaking would just sort of, let's try to make a movie. Yeah.
Well, you know what, though? I think it still counts as filmmaker because a lot of folks that maybe think of doing that stuff never do. So as far as I'm concerned, you're a filmmaker.
Yeah, when you pay the whatever fee for the contest, and you're like, okay, and you get everyone to show up, and then you're doing it, right? You kind of forced yourself to attempt to make a movie, no matter how, and they're always bad, like ours. Other people's were great. They were like, wait, what? But ours were always really bad, but we just had a blast because you solve all these little problems on the fly, and so anyway, that's the other thing that's fun about workplaces like this is, why. So why do you work at a startup? Yeah, sure, there's all the startup stuff, but the type of people you end up with are just really interesting. They have they do really interesting stuff with their time.
It's been funny for a team of our size that hasn't hit 100 bodies yet. It's amazing that every single person that starts, there's something just fascinating about their background or their hobbies or their skill set. Well, Chris, thanks so much again for being the first Physna employee that is on the Physna Podinar. I hope you'll consider joining us back again soon. It was great getting to talk to you here.
Hey, thanks, Jay. It was an honor.
Awesome. Thanks so much, Chris.
Welcome to Songs in the Key of Thangs. This month's feature is entitled From the Model to the Mind.
I was
All right, so thanks again so much for tuning in to the first Physna Podinar episode. Now, as I said earlier, please give us lots of feedback. Let us know who, when, where, why, or what you'd like to see in future Podinars. And one last very special thanks to Dr. Michael Grieves and Dr. Chris Roedig for joining me in this inaugural episode. So please check us out, Physna.com, and the social media links listed here, and we will see you next time.
Be sure to sign up for the Physna Balance monthly newsletter. And check us out on Spotify if you'd like to hear future episodes in legacy podcast format.